So in this video, we're going to be looking at reactivity of our alkenes. We're going to look at the three different types of addition reactions: halogenation, hydration, and then hydrogenation as well. Now, when we look at alkenes, they're going to be more reactive compared to our alkenes. Remember what we said, alkenes are unreactive for two reasons, because of course they've got high carbon-carbon bond enthalpies and high carbon-hydrogen bond enthalpies. These sigma bonds are quite strong, and then of course they're going to be non-polar as well. Well, when we look at our alkenes, they're also going to be non-polar, but the difference is that we've actually got a carbon-carbon double bond, and that double bond consists of a sigma bond, which is going to be one of them, and then of course a pi bond within it as well. Now this is going to be quite important because our pi bonds, we can say they're relatively weak, and our pi bonds, they're going to be of course weaker compared to our sigma bonds overall. So that's what makes them more reactive, and we can actually end up adding a molecule across the double bond. That carbon-carbon double bond will break, the pi bond will break, and of course we can add parts of a molecule to the actual carbon atoms within the double bond. Now this is a type of reaction that we call an addition reaction, and this is where two or more molecules, they combine together and they make a larger molecule. Now you can see here I've got an example of propene, and we can have the addition reaction of propene where I've got the carbon-carbon double bond over here, and we can see the carbon atoms within the double bond. We're going to add a molecule of XY, which is just going to be our general electrophile. The actual mechanism that takes place is electrophilic addition, but we'll come on to that in another video. But again, I'm taking XY and I'm adding it across this double bond. So I'll get rid of the double bond. Now carbon in each case is going to be missing one bond. One of them bonds to of course an X, so that's going to be carbon 1. Another one will bond to Y, that's going to be of course carbon 2. Now in terms of carbon 3, of course that's going to be untouched because that is where we have a saturated part of the molecule. The unsaturated part is going to be of course this region here where we've got the carbon-carbon double bond. Now there's two key points to mention when it comes to this reaction. The first one is that we actually end up with 100% atom economy, and that is because we are only forming one product. There is no waste product in this reaction in all addition reactions, and so we know the atom economy is 100%. Now if I were to look at the second thing, we know that of course in this reaction we actually have a saturated molecule over here that's going to be formed compared to our unsaturated molecule here as well. So technically what we're doing is we're saturating the actual alkene itself. And there's a second point there as well. Now let's look at some examples. The first one, the easiest one, is halogenation, where there's two actual types. Now the first type is when our alkene reacts with a halogen, and then the second type is going to be when our alkene reacts with a hydrogen halide. Now in both cases you actually form a haloalkane. In the case where we're dealing with halogenation, where we're dealing with, let's say, a halogen like X2, where X can be any halogen. So let's say if I were to look at the halogenation of propene, right, what I'm doing is I'm brominating it, that's another word, and you can see here I've got carbon 1, carbon 2 in the double bond. I've got carbon 1, carbon 2. One bromine atom has been attached to each carbon atom, and that's what we can see over here. And of course we just take some aqueous bromine or something like that, and we just mix it at room temperature and pressure. We don't really need to add any heat or anything like that. We don't need reflux. Of course we can do it if you want to, but it's not needed. And of course the temperature we would say is 25 degrees Celsius, which we don't even need to be able to say. It's just not room temperature, isn't it? Yeah, 298 Kelvin itself. Now another circumstance is if you were to react this with, let's say, a hydrogen halide, where you can see I'm reacting it with hydrogen bromide over here. So I've got the halogenation of propene again, but in this case, right, we're reacting it with HBr. In this case we end up with 1, 2 carbon atoms and then 1, 2 carbon atoms here, but on one of the carbon atoms we actually end up adding a hydrogen, which we can't actually see, and on the other one we actually add the bromine itself, because of course Ivron's skeletal formula, you can't actually see the additional hydrogen on there itself. Now with this reaction, when we react something with a hydrogen halide, what we actually end up with is, if we're dealing with an unsymmetrical alkene, let's say if I were to look at something like ethene, which looks like this, if I were to draw a line of symmetry down the carbon-carbon double bond, we've got the same thing on either side. But let's say if I were to look at propene, for example, we've actually got no symmetry over here. We actually end up with an asymmetrical structure, and so we can actually end up with a variety of different products. So yeah, in that case I can end up with one bromopropane, but then the bromine could have gone on the second position and the hydrogen would have gone on the first, and we can actually end up with another product which is going to be 2 bromopropane as well. So just bear that in mind. Of course you'll deal with this more when you look at Markovnikov's rule, but the mechanism for this reaction we need to be able to do as well, that's going to be electrophilic addition. Electrophilic because it involves an electrophile, and then addition because you're adding one molecule onto another. Again, all of the atom economies, they're going to be 100% themselves. So yeah, we're only forming one product, no waste product. So moving on, what about if we were to look at an application of this, well, we can actually add bromine water, which is just going to be Br2, and then it's going to be, of course, aqueous bromine dissolved in water. We can add it to a solution that contains maybe an alkene or doesn't contain an alkene, and what happens is if we've got a carbon-carbon double bond present, if we've got an unsaturated molecule, then of course our color change will go from orange to colorless, and that's what you can see over here in this test tube reaction. We're going from orange to colorless itself. Now what's actually happening is bromine is going to be added across the double bond, where I end up with carbon 1 and 2 over here. And then what happens is, of course, on carbon 1 and carbon 2, we add a bromine to each carbon. And so that bromine is now no longer going to be aqueous. It's going to be reacting with our alkene itself. Now, what about if I didn't have, let's say, a unsaturated compound? What about if I had a saturated compound? Or about if I had no double bond actually present? Well, we would see no visible change, but we also need to mention that the solution is going to stay orange itself. So, of course, the bromine is still going to be aqueous. It's not going to be added to make the actual haloalkane. So yeah, moving on, we're about our two other reactions that we need to be aware of. Well, one of them is called hydrogenation, where if you split up the word, you can see it's got hydrogen in it, and we take our alkene, we react it with hydrogen, and we form an alkane. Now the reaction conditions here is a heterogeneous catalyst, which is nickel, and a temperature of 150 degrees Celsius. And basically all that we're doing is we're trying to get rid of this double bond over here. So yeah, we've actually got here carbon 1, carbon 2, and to each carbon atom we're actually adding a hydrogen, which in skeletal formula you can't actually see, and so we end up with a saturated compound. The bond angles change. It goes from 120 degrees around the carbon atoms with the carbon-carbon double bonds, and it's going to go to 109.5 degrees itself. Heterogeneous catalyst, basically it's going to be a catalyst, the nickel, that's going to be in a different phase compared to the reactants itself. So yeah, there's one reaction there. Again, the atom economy is going to be 100%. Looking at our next reaction, we can take our alkenes in hydration, think wet, think steam, and of course we can react them with steam to form an alcohol, where of course it's not going to be water, right? We would actually have steam, which is going to be the gaseous form of water itself. We need to have a temperature of 300 degrees Celsius to get that steam. Of course we need a catalyst. In this case it's a homogeneous catalyst of either sulfuric acid, like most reactions are, or phosphoric acid. We also need a high pressure of 65 atmospheres as well. Now let's see, if I'm looking at the hydration of propane, this one's quite a hard one to visualize, but what I like to see is in terms of this addition, I've got 1, 2 carbon atoms, yes, over here, 1, 2 carbon atoms, yes, over here, but I'm going to have a molecule of water, which I'm going to draw out quite weird. It looks kind of like this. Of course I've rotated it around a bit, but of course I'm going to end up with my oxygen hydrogen bond breaking, and this hydrogen is going to be attached to, of course, this second carbon atom over here, and then the rest of it, this OH structure over here, that's going to be attached to this first one, and we end up making propan 1O. Now again, the actual positions at which the hydrogen and the OH joins flips, and we can actually end up with propan 2O as well, which is an isomer that can be formed from this as well. So moving on then, I've got a task for you to try. Feel free to pause the video and have a go at the following question in determining what the product is going to be in, of course, each of these reactions. So yeah, in this case, we've got, of course, I'm going to go with this one, chlorine. That's quite easy. I've got 4 carbon atoms. On carbon atom 2 and carbon atom 3, that's where we end up bonding our chlorines. So 1 chlorine per atom. I end up with, of course, it's going to be 1, 2, 3, 4. A chlorine is going to go over here, and a chlorine is going to go over here. There's the first one done. The next one, HI, I end up with 1, 2, 3, 4 carbon atoms over here, and then of course a hydrogen is going to go at the 2 position or the 3. It doesn't make a difference, and the iodine goes at the other position. I'm going to go with the iodine going here, because even if we got another product, let's say the iodine went on the 3rd position, we would still call it 2-iodobutane anyway. There's that one done. What about hydrogenation? That's an easy one. You just get rid of the double bond. That's quite easy. There's that one done as well. Look at the next one. We've got, of course, hydration. We've got steam, 300 degrees Celsius, 65 atmospheres. I'm going to end up with, of course, 1, 2, 3, 4 carbon atoms again, and then I'm going to end up with an OH here as well. Yeah, so of course I'm going to move that a bit to the side just to tidy it up a bit, but I end up with, of course, that one done as well.